Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Welcome to another episode of Machine Learning Made Simple. We have been talking about the DeepSeek models and doing a slight deep dive into the models. Not too technical, but the basic amount that everyone wants to know about what are the new techniques that makes those DeepSeek models so efficient and cost productive. So we're going to continue in that fashion. In the last episode, we talked about the earlier version of the DeepSeek models, which truly brought in the main innovations, and the main innovations were surprisingly efficient use of the GPUs, the graphical processing units, especially the NVIDIA GPUs that they use to train their models. The researchers essentially laid out the groundwork and said, hey, look, hey, when these large language models are being trained by these large corporations like OpenAI, Anthropic, and all those other Mistral and all of them, they're making a massive mistake by underutilizing these GPUs. So when you train a large language model on a GPU, half of the GPU remains unused, and there are many reasons for that. Let's say we have 1,000 GPU cluster. Let's say all NVIDIA 1,000 GPU cluster, the 1.2 trillion GPT model is loaded onto it in a distributed fashion. In addition to the model weights that needs to be loaded to the GPU, the training also needs to load the optimizer weights. It needs to load the gradients and something known as the velocity. So it needs to calculate all those values and store them just in case those values are needed when the data flows, both during the forward pass and then during back propagation, when those gradients are used to fix those values. Imagine the forward pass is the model learning the data and making a prediction, and then there is a loss function at the end which says, okay, your loss is massive, and then back propagates the loss to make those error correction. So imagine you're trying to throw darts at the dartboard and you missed, and you see how much you missed by, and then you send the signal from your brain to your hands to make that adjustment to make the next shot more accurate. So that's the same thing is happening. Those adjustments are essentially what flows backward through the network, the deep learning network, and essentially provides that update to the weights, which slowly and surely makes the model more and more accurate. So that's the whole process of the model training, and there are a few adjustments here and there, but that's the whole process in gist. Now what happens during this process is that they do need to store the optimizer weights, but what happens in this whole process, let's say the model has 3,000 layers. Now these 3,000 layers would be distributed across, let's say, 1,000 GPUs. Now each GPU will host 3 layers each. Now as the data flows through it, let's say during the forward pass, the first GPU performs the forward pass, and then the data moves to the next GPU, which has the next set of 3 layers. Now what is happening with the first GPU is staying idle. So when this training process happens, only one GPU is active and all of the rest of the GPUs are sitting idle. Imagine we have 1,000 GPUs, and that's actually less. Like these farms usually have 50,000 or 100,000 GPUs working together. So let's take a realistic number. Let's say we have 100,000 GPUs and only one GPU is active during training. I mean, it doesn't take a PhD to figure out that this is tremendously inefficient. So what happens in this whole training pipeline, as the first batch of data moves through the GPU cluster, let's say we have 100,000 GPUs, and let's say first few hundred GPUs have already processed that batch of data. Now that batch of data is now distributed, let's say from GPU 100, so let's say GPU 2000. Now the first 100 GPUs are now sitting idle, but GPU 100 to GPU 2000 is working, but then every other GPU from GPU 2000 to GPU 100,000 is sitting idle. So essentially it creates a bubble of work. So this is called a pipeline bubble. This is named by NVIDIA engineers who first observed it, and this bubble essentially moves along that GPU cluster pipeline. Only work that is done is around that bubble, and all the GPUs remain idle. This is tremendously inefficient, and there are ways around it, and pretty sure OpenAI eventually addressed this. But when they first implemented their GPU training and they scaled up with thousands and thousands of GPUs, their main cost was these kind of inefficiencies, which were not discovered till recently. So that is why the cost of training of those original OpenAI models were so high, because these inefficiencies were not detected and addressed at that point. So DeepSeek was fortunate that these inefficiencies were detected by the time they started the training process, and they used something called the one forward and one backward pass, which makes sure that when the forward pass is happening, those other GPUs which are sitting idle, they just don't sit idle, they start doing the backward pass. Let's say in an assembly line, the car parts are moving forward and people are working on it. So let's say the chassis has moved forward and some people are working on it, and then the people who have already worked on the chassis can now start working on, let's say, exhaust manifold, right? So there's the same thing. So give the GPU some extra task while it is sitting around and doing nothing, and that caused a substantial reduction in compute costs, because instead of training 100,000 hours like the original models of OpenAI, they cut it down to say like 100 or 200 times, because this is the whole pipeline is now extremely efficient. And not only this, there are a few more optimization that they added, and we are talking about the earlier version of DeepSeek models. This is not even version 2 yet. So these are earlier versions of DeepSeek model which introduced this optimization, and if you're interested, go back to the previous episode where we talked about these things in more detail. So but that is the main overview. So the pipeline bubble is completely eliminated, and that reduced their training cost by a huge margin, and that really gave them the edge because their training costs are substantially lower. Recent blog post by Dario Amodei. He is the CEO of Anthropic. The Anthropic is the company which has brought out those consumer models like Claude, Sonnet, and Haiku. Those are excellent code generating models, even better than OpenAI. In fact, he mentions that in his post. The whole point he's trying to address is that people are going crazy about these cost efficiencies of DeepSeek over those consumer grade models like OpenAI and Claude. However, according to Amodei, this was supposed to happen. And in fact, he talks about this at length because of the scaling laws and the way things progress. What he says, if you read his post, he will say that the number is around 4x a year. So costs to train any model, any machine learning or large language model drops by 4 times every year. And there are many reasons for that. One of these is those researchers finding those inefficiencies and fixing them, and all the issues that were found during the training process that feeds into it. So four times reduction in cost per year. Amodei is saying that he refused to give the exact number for cost for training the Claude Sonnet model, but he said it's around some multiple of 10 million. So I'm assuming it's like around the 60 million, 10x cheaper than the original OpenAI model. And they're saying, Mark, that's the scaling law, because the top line Claude models came out around 2.5 years of the initial OpenAI model, so it should be like around times 2.5, so around 10x reduction is what is expected. What Amodei is saying is that Claude was actually more compute efficient during their training, because they were expecting around 8x reduction compared to OpenAI's training costs, but they got 10x reduction. Amodei is saying that has a better compute efficiency than people are talking about DeepSeek, because DeepSeek was supposed to have that 4x. So if Claude was trained around, let's say $40 million, let's take a rough number. He didn't give an exact estimate, but let's say 40 million. So we assume that between 40 million and 60 million. So let's divide it by 4. So we are assuming that that DeepSeek should have cost $10 million. So DeepSeek claims it trained with under 5 million, but that's only for version 3. So there are other models, the reasoning model, that also cost a little bit more. DeepSeek also doesn't mention in their technical article how much their GPU cluster costs. They only talk about the cost of training. Now there is also the cost of knowledge distillation and dataset preparation. That is an extra added overhead that doesn't get mentioned. People hear 5 million. Yes, it did cost to do the actual model training, but there are other overhead costs that Amodei is saying that it's just the compute cost of the training the final model for the final run. that is not just a cost. Dataset gathering, dataset cleaning, dataset preparation, knowledge distillation from a superior model, which people claim DeepSeek our researchers have done. And we'll talk about the distillation process and how people are saying they have distilled OpenAI's models. DeepSeek's model is also kind of old. Like, that model is comparable to what Claude or OpenAI was 7 to 8 months earlier. So that being said, that 4x cost estimation is kind of generous, and maybe it should have been more. That being said, DeepSeek does have access to over 50,000 chipsets, like GPU chips. So, and that's a huge number, and that itself, by people's estimate, costs around $1 billion. And this only plays into the exact scaling laws. Like, if OpenAI had spent $100 billion on their chips, and then Claude spent $10 million, and then now DeepSeek spent $1 billion. So the scaling laws are being respected here. And what Amadei is saying is that there's nothing to be going gaga about. These are the scaling laws that are expected. If some other company like Mistral came up with this, of course Mistral already has that cluster, or there, let's say, a new AI company who can come up with similar model with similar reasoning capabilities, it will also cost them $1 billion. It's nothing new that is expected, because their optimization is not good, which I don't agree with, because I have seen the optimization. These optimizations were not present. So just by saying that the scaling laws have been honored and therefore we should not be surprised they did nothing fancy, that is not the right thing to say at this point. And the reason is simple. Let's say the scaling laws are respected. The reason the scaling laws have been respected, because those innovation, those optimization have been added. What Amadei is saying, that if DeepSeek researchers have not added those optimizations, if someone else came up with similar model at current time, they would have added those same optimizations, which I partially agree. But remember, those optimization were already added to DeepSeek version 1, which they didn't call version 1, they just called DeepSeek LLM. Innovation that they added, which no one thought about, is multi-headed latent attention, which we are going to talk about today. Similar, and that is what caused that 95% drop in memory requirements. But before we can talk about that, let's look at the political angle that these consumer grade companies are really harping on, especially OpenAI and Anthropic, because their business has been challenged and is under severe threat. Because if DeepSeek API costs 95% less, I mean, people don't care. People have outsourced their manufacturing to China, for example, just to reduce costs. I mean, stops these software companies who don't have like large secret regulatory compliant architecture, like small startups or people who are not in the highly regulated sectors. They can easily outsource. It's just a switch of the API. It's like one line of code, and even the CEO can come in and change it. Like, it doesn't take a machine learning engineer to replace OpenAI by DeepSeek API. It's very straightforward, and it's 95% cheaper. And I'm pretty sure almost every single mid-level, mid-sized business CEO has already made the decision to switch to DeepSeek. I mean, unless they are under regulatory restrictions, that because they are concerned about data leak. I mean, data leak is a major concern. You don't want your data to go out of your country. I mean, if I, for example, wouldn't do it, I will still pay more money to OpenAI APIs for my inferencing purposes, for my architecture. But that's just me. I don't like my data going out. It causes whole list of problems, audit trail issues, enterprise architecture modifications that needs approval from an architecture review board, and all those things. If you're part of a big organization, those changes just cannot be done so easily. Small and mid-sized businesses, which mostly primarily run by a CEO with very few passive investors, they have wide latitude in making these decisions, and they are switching to DeepSeek. And that's the main concern, because these mid-sized businesses were the bread and butter of these OpenAI models, because they use OpenAI almost exclusively. So they're losing business, and they are causing a lot of noise. They're creating a lot of noise because they're losing business, and they're crying foul play that they're saying that these DeepSeek researchers have distilled the knowledge of their own models. And knowledge distillation is pretty straightforward. You have a teacher model and you have a student model. The teacher model teaches the student model answers answers that it doesn't have access to, or it hasn't seen it in its training data. And if I asked a more nuanced question like what is the black hole entropy for a 5-dimensional black hole, that would be a very difficult and specialized subject which the small language model probably will not have the answer to. So now get the bigger model like OpenAI model to answer that, and then have the smaller model memorize the answer. The smaller model is distilling the knowledge and essentially memorizing the answers that the big language model is giving it, and then it has all the answers that it expects the user to ask it. So that is knowledge distillation, and it can be efficiently performed if you can make substantial amount of calls to any of those OpenAI models. So if I have a small model that I'm training, let's say in black holes, then I don't have the resources to consume that much training data. So what I'll do, I'll create a bunch of questions. In fact, I'll ask OpenAI to create all possible questions, create a synthetic data set and give it to me, and then use that synthetic data set from OpenAI to train my small language model, which will then send those API calls to OpenAI to refine itself over time. This is essentially a coarse-grained knowledge distillation. Now OpenAI is saying, and also Anthropic is saying, that this process is being used by the DeepSeek researchers to distill the information out of OpenAI and into DeepSeek. Now there are two arguments that are people coming up with. So I am hearing many people are saying that OpenAI and Anthropic really don't have a higher moral ground because they themselves have scraped the internet and consumed massive amount of intellectual property. And in fact, there are many intellectual property lawsuits against most of the companies, like consumer good companies like OpenAI, which are still in progress. So they should not be saying that DeepSeek has distilled their knowledge. And I personally think that the burden of preserving their own intellectual property really lies on Anthropic and OpenAI. People from which OpenAI and Anthropic allegedly took the intellectual property, they had no way to stop that, because if someone posts their songs online on their YouTube channel or their podcast is open for grabs, they probably have a disclaimer that do not monetize this is my intellectual property. But OpenAI and Anthropic allegedly didn't respect that. Now the people whose intellectual property got allegedly scraped by Anthropic or OpenAI couldn't stop that from happening. Being said, OpenAI and Anthropic both have the capability to prevent that intellectual property theft. And this is what I believe, because if we see a high spike of API usage from a Chinese company, it is very hard for me to believe that they don't have tracing going on. If I use too much OpenAI's API, I get blocked up. I have got blocked up at 2 o'clock in the morning from overusage. I mean, it's not fun. Like they can block consumers so easily, and it's hard for me to believe all those tracing and all the data that OpenAI gathers, they are not able to detect that massive usage coming from China, from those DeepSeek research group. I mean, it's almost unfathomable to believe that they let it happen. The clear explanation might be that they probably thought that they are using it. They are probably not going to much better than what the version 2 was, which was not very good. The DeepSeek version 2 came out around August, and we'll talk about that today. And it was not that good, but it did implement a massive change, which was the multi-headed latent attention get. But even with ML, multi-headed latent attention, their model output didn't come even close to Anthropic and OpenAI's models. I think there's a little bit of hubris there on part of OpenAI and Anthropic. They didn't realize their next model would be substantially a quantum leap ahead and almost would catch up, at least in the public's opinion, to the OpenAI reasoning model. So they probably didn't expect that, so they let them consume so much of their data, and now this is where we are. So that's pretty much my 2 cents. So Amadei goes on and explains few other topics, which clearly is his perspective, which I respect, and he's probably right on many of those things. One of the things he said in the footnotes, which I really agree with, so he says that I suspect, this is by Amadei, he says, I suspect that one of the principal reasons R1, the DeepSeek R1 reasoning model, gathered so much attention is that it was the first model to show the user the chain of thought reasoning that the model exhibits. You have used the DeepSeek R1 model and you ask it a question, what do you think would be the ideal career choice of someone who have studied physics, right? Then it thinks for a while, and in fact OpenAI reasoning model also thinks for a while, but it doesn't show us its chain of thought. But DeepSeek R1 model does show people the chain of thought, so people realize, oh, it is a superior model. In fact, all the commercial models have chain of thought reasoning built into it. In fact, we talked about in one of the earliest episodes of this podcast, chain of thought reasoning was quite new then, and we talked about it, and it was easily implemented in a RAG pipeline was quite hot at that back when we started this podcast. And we got great results by using a chain of thought reasoning process, and it was very easy to implement. Eliciting a chain of thought response was quite easy to implement. If it's easy for a consumer to do that, guess the enterprise will definitely implement it. So chain of thought was part of all OpenAI and Claude models for a really long time. They just didn't show that reasoning process, the thinking out process, and did not display that to the user. DeepSeek does display it to the user, and Amadeus is saying, and which I partially mostly agree, that might be one of the main attractions to reasons, that they can see the reasoning process. And in a response, OpenAI quickly added that reasoning thought process to their O3 mini model, and you can use it and you can see that it thinks and gives you the reason why it thinks. So they caught up pretty fast. However, what they could not catch up with is the price. It's 95% cheaper, and the reason is 95% cheaper is what we're going to discuss today. Now let's take a quick technical deep dive into the DeepSeek series of models. We already discussed the DeepSeek version 1 model in the previous episode. So now we're going to continue with the version 2 models. And since version 2 and version 3, which is the current iteration of the DeepSeek model, are so similar, we're going to do them together. In fact, if we discuss version 2, we pretty much discussed version 3, but version 3 did introduce substantial amount of technological innovations, but most of the technological innovation, at least most parts, are so technical. In fact, they are mostly hardware based innovations, so we are not going to go too deep into that, but we are going to mention that. So let's start with the DeepSeek version 2. This came out around June of 2024. And I'm going to quickly read the abstract, which is quite self-explanatory. They say we present DeepSeek V2, a strong mixture of expert language model. Now, if you don't know what a mixture of expert is, essentially what people do is that if they say that, oh, we cannot get any better reasoning capability, any better performance capability from our large language model, why don't we mix 2 or 3 of those large language models, combine them and create a mixture of expert? So what happens is that the model is specifically trained by having multiple experts. Let's say one expert can be a grammatical expert, one expert can be expert in phrasing, one expert can be an expert in translating. So it can have multiple large language models. All those experts can be combined, and then they will be combined strategically so that the lower layers, the main training layers, get combined, and the final layers, that's where the experts come in, because that's specialized knowledge. As an analogy, let's look at the medical profession. We have all kinds of different experts, like pediatrician is specialized in child care, a surgeon is specialized in surgery, orthopedic is specialized in anything bone, and ENT is specialized in ear, nose and throat. So there are very specialized knowledge, and all these doctors have specialized knowledge. But if you look at the courses that they have taken, starting from their college, bachelor's degree, pre-med, and even till very last few courses before even starting their residency, most of the 80% of the courses, initial courses, are pretty much the same. The main bifurcation for these specializations of these medical professionals happen at the final stages, and that's the same thing that happens with mixture of experts. The initial layers are all shared because they are learning the same representation, latent representation, but when it comes to the final representation, that's when the knowledge bifurcates between these experts, and that's exactly what is happening here. The model has 236 billion total parameters, of which only 21 billion are activated for each token. It means that the model is routing. It's choosing some of the experts and it's not activating all the experts. So if it has 236 billion parameters and only 21 billion are activated, so that's 1/10, which means, let's say there are 10 experts, it is choosing 1 out of 10. That reduces the model load. It improves inferencing time because only a small part of the model needs to be loaded in memory, and there are only few amount of experts who are chosen to perform the inferencing, so the throughput is extremely high. So that's already a speed up in inferencing speed right there. But this is already implemented on those enterprise grade models like OpenAI and Anthropic, they've already implemented these kind of advanced optimization technique for their mixture of expert models. And OpenAI is definitely a mixture of expert model, and Claude is also, in fact, all enterprise models that are out there, most of them are a mixture of expert models. Otherwise, you cannot get that level of understanding. It's impossible to expect a large language model to be good in reasoning, in doing math tasks, and in generating images, in coding, in all those things. A single large language model probably will not be that good. And we talked about this before. All of those are of experts, and they have an expert router which routes those questions to the right expert. So the second thing that we need to focus on in the abstract that they mentioned in the DeepSeek version 2 paper, that they say that the pre-trained DeepSeek version 2 on high quality and multi-source corpus consisting of 8.1 trillion tokens and further perform supervised fine-tuning, and this is the crucial part. They perform both supervised fine-tuning and reinforcement learning to fully unlock its potential. Nothing fancy. Supervised fine-tuning has been done for a while now, and so is RLHF, reinforcement learning with human feedback, to perform model alignment. The whole point of performing SFT, supervised fine-tuning, and RLHF, reinforcement learning with human feedback, is to align the language model responses to human values, in not to behave toxic, not to exhibit toxic behavior. For example, we heard of Tay, which was a chatbot released by Microsoft. They didn't put any guardrails around it and just released it. It exhibited extremely toxic behavior and started exhibiting anti-Semitic behavior within a few hours of it going live. A lesson from that is to align the model responses to human values, societal values, so that the responses are kind, reasonable, and does not have toxicity. And toxicity is a measurement that is performed by human annotators. There are machine learning models which can detect toxicity at all, but those models has to be trained separately. But SFT and RLHF has been done for such a long time. There's nothing to brag about. So this is not one of the main things that people are excited about DeepSeek, but what they're really excited about is the 95% efficiency, and they quietly put that right next to the abstract without actually saying anything about it. So what they didn't say explicitly in the abstract is that they implemented multi-headed latent attention. So they replaced the multi-headed attention, which was originally implemented in the Vaswani et al. Attention is all you need paper, which essentially brought the transformer model to the forefront of the public, to the front of the public. So they replaced that because multi-headed attention consumes too much resources, too much memory. Most of the memory of a large language model, especially during training, is consumed by the multi-headed attention layers. So in order to mitigate that, they took that and converted those to latent representation. So as you know, latent representation is a very low dimensional representation of the same thing. So if I take an image of a cat and do a latent representation, if let's say the JPEG image of the cat was taking up 2 megabytes, the latent representation may take up 1 or 20 kilobytes. Using latent representation is essentially compressing those memory requirements to a very tiny value. And in fact, the amount of compression is close to 93.3%. So that's where the 95% efficiency comes in. And there are other things also that optimization also that factors into it. But the main innovation for DeepSeek version 2 model was the MLA, multi-headed latent attention. And this is where it got very exciting. To understand what multi-headed latent attention is, we have to go back to what multi-headed attention is to begin with. So this was introduced in the famous Attention is All You Need paper by Vaswani et al. This is the paper that started the transformer revolution. So what is the multi-headed attention and why is it used? In the seminal paper Attention is All You Need, which really started the transformer revolution, and multi-headed attention is the core of the transformer architecture. Previously, the way these autoregressive models, the generative models, were working was they will ingest a token or a word one by one, and then they will spit out the response. So it will first generate a word like the quick fox jumped over the brown dog. So let's say it's starting to generate then it will look at its probabilistic model and okay, so maybe the next word might be quick, maybe the next word is fox, so it will slowly generate one by one. But with multi-headed attention, what it can do, it can take the entire, consume the entire sentence, and then it will cross correlate each part of the sentence with each other. So it will ingest the sentence and create 3 different matrices or numerical representation of the sentence into 3 different big matrices, and then cross correlate 2 of them. That quick fox, quick is an adjective to the fox, and brown dog, brown is an adjective for the dog. So it will give attention to these 2 words, quick and fox, and brown and dog might go together. And it also pays attention, long range attention, to the fact that the fox is jumping over the dog. And this attention layer comes in from something called the KQV value, query key value pairs. So these are the 3 matrices I just talked about. Take the sentence, create a numerical representation called query key value, essentially do some matrix manipulation, and essentially what you can calculate is a correlation matrix which highlights that which words go together. Like the fox and jumping over the dog, these go together, but fox jumping over the mountain probably doesn't go together, and it will learn it once it ingests enough amount of documents and tokens. So this was multi-headed attention. Now, in order to save space, because as you can imagine, each token will be converted into 3 different matrices and then all kinds of matrix multiplication, it will become huge, right? If I have a simple 10 by 2 matrix which multiplies a 10 by 2 matrix, I get 10 by 10 matrix. Okay, so now it's certainly big. It consumes tremendous amount of memory. So in order to conserve memory, people came up with a few different innovations. One is grouped query attention, where some of the values and keys are grouped together, and those queries which come in the sentences that are being learned by the model, they are the matrices which are not grouped, and then they share the keys and the values. It works to a certain extent. For example, sometimes some of the key values are shared, like if we have the same sentence, most of the words in the sentence will probably share the key values and the keys. However, it's not the most efficient. So this is where the latent attention mechanism comes in. So the main matrices which can be shared are the keys and the values, and those also are the ones which consume the most amount of memory. But queries we cannot do away with. We need those query matrices because those queries are coming from the user or the training batch, the words that the model is ingesting. So we cannot do away with those matrices. We need those matrices. So in order to reduce the space memory requirement, a brilliant idea is to take those keys and values and project them into a lower dimension, essentially find the latent representation of those matrices. And this is done especially in image analysis. In units, if you look at the unit architecture, that's essentially what is done. Sequentially lower and lower dimensional representation of an image is found, and then it tries to recreate from that latent image. It's a beautiful idea and it works. So the latent representation is a lower dimensional, smaller memory footprint representation of any matrix that is used in simplifying, that is essentially used to simplify the whole process and reduce the memory footprint. And now you might ask, how much does it reduce? What is the optimization cost? So the total reduction is around 93%. So it can reduce memory usage by 93%. And this is where close to 95% of the optimization of the DeepSeek models come in. But at least I believe that that's where it is coming from. In addition to all the other optimization, severe memory optimization and extreme pipeline optimization during inferencing and training time that they have built in, so that no GPU goes idle, especially the routing, they have also optimized it, which we'll talk about soon. Now let's talk about the drawbacks of using this latent representation. In the original implementation of the transformer architecture with the multi-headed attention, not the latent one, the multi-headed attention, even though it consumed a lot of space, it had one drawback as well. And main drawback was that there was no positional encoding. For example, if the sentence was the quick fox jumped over the brown dog, then it can do those attentions between and to find the correlation between fox and the brown dog. However, it doesn't know in which order they appear, because the order in which these tokens are fed, that order is gone. It only has the correlations and which one has high correlation with what. That's only the correlations exist. But as you know, if you're finding correlation between 2 parameters, x1 and x2, the order doesn't matter. So therefore, the the matrices don't know in which order the words appeared. This was not a problem with the RNN model, the recurrent neural network problem, because they generated those words, those tokens, in a consecutive fashion. So they knew in which order the words were either ingested or generated. So the ordering was not a problem, but the ordering is now a problem with transformer architecture. So in order to get around that, the Vaswani et al., they suggested that why don't we encode those positions of those words and feed it back with something known as positional encoding. So they fed back those positional encoding and merged them with those matrices, right? So now the same thing could be done with multi-headed latent attention, but now the challenge is the matrices for the positional encodings are still in higher dimension, but now those matrices have been those latent matrices have been projected to a lower dimension. So in order to recover the positional embedding, either the positional embedding needs to be projected into a lower dimension or vice versa. So that creates a challenge. So to get around that, what they did some mathematical trickery where they did multiple layers of positional encoding, which fixes the problem. So essentially it's just pure math. If you're interested, go look at the paper, but that's the main issue with having a latent representation, that we have to do some extra matrix multiplication to go get around that. So the 90% reduction in memory comes at the cost of extra computational cost. We are willing to pay higher computational cost to save 90% of the memory consumed by these multi-headed attention layers. So that was the main innovation that really drove the DeepSeek models to extremely high efficiency. Now there are a few other things that they implemented, and this is normal mixture of expert model, but I'll just mention it. In a mixture of expert, let's say we have 10 experts, but at a time we don't want to route all our words or tokens to all those 10 experts, because then we're consuming way too much resources. We only need 1 or 2 experts to really do the job. So let's say someone is asking, tell me how to differentiate between a common cold and flu. Let's say we have an LLM, which is a medical LLM, and it has 10 medical experts. And I'm not going to list all 10. Let's say one is like a very general physician expert, which can respond to most common question. And then there is cardiologist, oncologist, endocrinologist, orthopedic, and there are a few other different experts, right? So now when a question comes in, how to differentiate between common cold and flu, in fact, all the experts can answer this question, but we can easily send it to one of those shared experts, which is the general physician can respond to that question. But when a question comes in, so what causes atrial fibrillation, then even though most of the physicians can respond to that, it's better to send it to a cardiologist to get a better nuanced response. So you see where this is going. The correct expert is chosen depending on the expertise level. So then there is other MOE architecture, the mixture of expert architecture, which performs load balancing. So essentially there are 2 ways to handle this mixture of experts. Either we can choose experts based on their expertise, or we can just perform load balancing, see which expert is really sitting idle and just give it to those experts. So if there are like 4 experts and 2 of them have been loaded with tokens, and the next set of tokens should go to the next set of experts which was sitting idle. Now there are a couple of ways of doing this. Both of these methods have their merits and demerits. Now the first method, where we choose the right expert, can be achieved by training a router LLM, which looks at the tokens and decides which expert it's going to route to, which means we have to train the router layer as well, which will pick the right expert. So one way to do that is to, in addition to the loss function, and as you know, any machine learning training involves a loss function where there is a predicted something, some prediction, and it gets matched with the expected result, and there is a difference. If there is a difference, then that is called the loss, and that loss gets backpropagated. So we can use and leverage that loss function. Now we're going to add a loss function for the router part as well. So if the router makes a mistake and chooses, let's say, the orthopedic to answer the question about the cardiac problems, or answer question about the heart instead of choosing the cardiologist, then that will penalize the router. But if the router chooses the right expert, let's say chooses cardiologist for the question about the heart, then the loss is almost minimal and the router has probably learned how to pick the right expert. So that's one way of doing it. Another way of doing it, like we said, that instead of having selective experts who can only do one thing, we can have experts who are kind of generalist, and then we're just going to load balance. So the next method is essentially load balancing. We don't want any of the experts to be overloaded, which essentially causes mode collapse. It's called mode collapse. We don't want that kind of things. Like sometimes the model might, or the transformer architecture might think, okay, they have overtrained one of the experts and then they realize that expert's output are the best. So the router keeps sending the same expert all the prompts that are coming in. So which means it gets trained over and over again and overloaded, and the other experts are not get trained at all. So think about this. Let's say you have a team that you are training, and let's say one of the students are really good and they get really better, and you don't want to give the same person, the same team member, the tasks to perform over and over again. They'll get better at the expense of others. No, you as a coach, if you're a coach, then you want to distribute the load, even though the others might perform poorly compared to that one expert who is getting better very fast. You want to distribute so the other team members also can perform and bring up their performance level. So that's essentially what the load balancer does in a router LLM. So there are two modes of operations, and DeepSeek version 2 chose the first way of doing this. Now that was all pre-training and training phases of the DeepSeek models. They also performed substantial amount of pipeline optimization. They implemented something known as dual pipe. Actually, it reduces the pipeline bubble that we talked about. Training happens only in a small batch. So let's say you have a layer of GPUs, 1 to let's say 100,000 GPUs. Your training batch progresses in a small bubble of let's say 10 GPUs, and all other GPUs stays idle. So that's a pipeline bubble. It completely eliminates that pipeline bubble and makes sure that all the GPUs are working all the time, reducing those overhead costs. So now, in addition to that, they also do post-processing for model alignment, the response alignment. And there are a few ways to perform the alignment. One is supervised fine-tuning, where you have a bunch of human annotated examples or question and response pairs, and you give the LLM the question and you see the response, and then you make sure that you penalize it for deviating too much from the response. So for example, we can ask the model, give me the recipe of an ice cream. Now if the model's response is rude, who wants to make ice cream on their own? Go buy the ice cream from store. That's a rude response. We don't want that response, so we're going to penalize that. So that's a form of supervised fine-tuning, not exactly, but it is a form of supervised fine-tuning. So then the other one is reinforcement learning with human feedback. So now that is a slightly more involved topic, and if you're interested, go look at my earlier podcast on the reinforcement learning with human feedback. Now, however, that being said, what I didn't discuss, and these people have implemented something known as GRPO, or Group Relative Policy Optimization, not to be confused with TRPO. Now, GRPO and TRPO are very similar. In fact, GRPO is an extension or generalization of TRPO. I'm not going to go into that too much right now. I'll probably do a separate reinforcement learning episode, and we are slowly going towards talking about DPO, PPO, and this comes after that. So we're going to talk about when we talk about trust region policy optimization. In fact, those are all on policy topics, and we're going to talk about that during our reinforcement learning episode. So for now, I'll just say this is a very advanced optimization technique, and it uses essentially takes the model and it has human preference model. Human beings gives feedback, and that has a certain probabilistic distribution. Now the model generates some output that has some probabilistic distribution. It calculates the difference in those probabilistic distribution and forces the model distribution to go towards the human distribution. So essentially it uses reinforcement learning to push the model distribution towards the human preference distribution of the human preference output. So when we talk about the R1 model, we'll see that the model exhibits substantial emergent properties like almost like sentient properties when just pure reinforcement learning is used. And in fact, there are a flurry of paper recently which talks about the difference between SFT and reinforcement learning, and the gist is very simple. SFT, the model essentially memorizes the answers, and with reinforcement learning, it essentially generalizes and learns how to do things, like forces the model to shift its distributional patterns too close to what is expected. And we'll talk about this and when we get there. For now, this was essentially what the whole deal about the DeepSeek version 2, which came out in July of 2024. And now we have a sufficient groundwork on which we can build the version 3. Version 3 essentially builds on version 2, but it made so many extra optimization, it's just mind-boggling. Now let's talk about the version 3 model, DeepSeek version 3. This came out in December 2024, late December 2024. So this is also a mixture of expert model like DeepSeek version 2 that we discussed in the previous segment. The difference is this is a much larger model. This is a 671 billion parameter model compared to the around 236 billion parameter of version 2. And at a time 37 billion is only activated, and we talked about this because it's a mixture of experts. Not all the parameters would be activated all the time. It's only a fraction is activated, is either usually it's 1/10 of the total number of parameters. In case it looks like it's 1/20th is activated, which shows that the model has a lot of efficiencies and optimization built into it. And as usual, they also mentioned that they have inbuilt multi-headed latent attention, just like version 2, and also the DeepSeek MOA architecture, which was already implemented into version 2. So what is new in this? So the new thing that has come into this version 3 model is remarkable. It's very technical, but we will look briefly along what are the main technicalities without going into too much detail. So one thing we'd like to mention before moving into the nitty-gritties of the DeepSeek latest model is that they claim that they used 2.8 million GPU hours. Now, how much of that is true, we don't know, and no one knows. That's their self-reporting. So, but this is quite low compared to OpenAI training hours. Although the exact number of GPU training hours of the OpenAI models or Anthropic models are not known, it's probably 10 or at least maybe 100 times that. So maybe it's around 270 million GPU hours, or maybe more. No one knows because OpenAI doesn't publish the exact GPU training hours. Okay, so what is new in the version 3, the latest DeepSeek model? Immediately something that will catch your eye is that they are now using floating point 8 mixed precision training. So that's revolutionary, and their rationale is very simple. They are saying, look at those stable diffusion model, look at those LoRa's. People are quantizing large text to image models and fitting them into consumer GPUs with very low precision, and it works. If a very low precision model can generate such fantastic images on a 12 GB consumer GPU, then why can't we perform the same training for a large language model with a lower precision? And in fact, they are right. They're saying model accuracy is not compromised if we use a lower precision. 32-bit precision is not required. Is that what they are saying? And they are probably right. So there you go. They went from floating point 32 to floating point 8. So that's a 4-factor reduction in memory requirement. However, they do mention, and we'll talk about it later, is that not everything can be used with low precision, because there are certain things that needs high precision, especially the attention layers. However, most of the model weights can tolerate very low precision and still perform on par with high precision counterparts. And in a substantial departure from the earlier version 2 of the DeepSeek model, the version 3 has moved away from the expert router choosing paradigm to a load balancing paradigm. So initially, as we discussed in the previous segment, the load balancing was achieved by a router structure which was trained to select an expert loss function. Now that prevents a mode collapse. So essentially not one expert gets trained forever and at the expense of the other experts. However, that does introduce some of the gradient instability, because now while the model is training and the loss function is training the model weights, router loss function comes in and messes things up. It helps train the router, but it's unnecessary extra appendage that we don't need. In fact, there is a very famous paper which these people realized that we don't need the loss function. It's essentially what they're saying, you don't need to use loss function. The moment you introduce extra loss for the router, it goes and conflates the loss function that the model is training on, and the model get confused. Okay, is this the loss for the expert model, or is this the loss for myself for train my own weights? So that causes massive amount of confusion, and research essentially shows that loss-free balancing is much better. Yes, you don't get those fine-grained expert choosing capabilities, but we have much more stable routing. So this essentially balances the expert load. And if you look at the gating mechanism, is very simple. Like all we have to maintain is 4 registers, which they call expert bias. Let's say I have 4 experts, 1, 2, 3, 4. Then if 1 and 2 have been taking heavy load, then the bias of expert 1 and 2 will go negative, and bias of expert 3 and 4, which has been sitting idle, will go positive. So in the next batch, expert 3 and 4 would be loaded, and 1 and 2 would be sitting idle and get some much needed rest. So that's how it essentially works, and the algorithm is very simple. Essentially it calculates the average number of tokens passing through the network, or essentially what is the load, and see how many tokens are processed by each expert. So let's say they're average 50 tokens, and let's say expert 1 has processed 80 of them, then its bias is already high, so it gets negative of that, so it gets minus 30 now because it is over processed by 30. While let's say expert 3 has processed only 20 tokens when the average number of tokens processed by the network is 50, so it's now has processed 30 tokens less, so its bias goes up by 30. So next time definitely expert 3 is going to be chosen because its bias is positive 30 compared to negative 20 of expert 1, which is now going to sit idle and take the much needed rest. And in addition to this load balancing technique, the auxiliary loss-free load balancing that the DeepSeek version 3 adopted, they also adopted the multi-token prediction. And now I'm not going to go into the multi-token prediction. It's a slightly involved. Essentially, it uses multi-heads to generate multiple tokens at once. We covered this when this paper first came out in, I think, June or July. So it's a very straightforward that we have multiple heads and it's generating multiple tokens at once. It's essentially having the transformer on steroids, like in the transformer generate multiple tokens simultaneously at once. Let's say we ask the large language model to write an essay on Einstein, right? So let's take a simple large language model which will go sequentially, one at a time, one token at a time, or one word at a time. Token and word would be used interchangeably, even though they're not always equivalent. So let's say it generates these sequence of words. Einstein was a revolutionary theoretical physicist. Now these are the tokens that are generated in sequence. Einstein, then was, then revolutionary. These are generated in sequence. So if we are using multi-token prediction, guess what? And we have 4 attention heads. Einstein was a revolutionary. These 4 words will be generated simultaneously at the same time. Now there are certain nuances when some of the expert might generate a wrong article. Then there's some mitigation techniques that are built into it, but that's the main idea, that 4 tokens, 4 words would be generated simultaneously. See how much the speed up is. If we're generating 4 words simultaneously and we have to generate a 400 word essay, then what will take, let's say, 100 seconds, let's say 1 second per word for a regular large language model to generate. Large language model multi-token prediction, which is on steroids, will do it in 1/4 the time because it is generating four words simultaneously. So instead of taking 100 seconds, it can do it in 1/4 the time, which is 25 seconds. Look at the speed up. So that is what DeepSeek implemented. That's why its responses are so fast compared to O3 models. And you might have noticed that O3 mini is quite fast, and pretty sure O3 mini have finally started using the multi-token prediction, but this was implemented by DeepSeek already. They also mentioned knowledge distillation, and we're going to keep this for the end because this is not too technical, but this is something we want to discuss when we're going to discuss the DeepSeek R1 model, which is a reasoning model. So when we look at the architecture for the DeepSeek version 3, nothing much has changed from version 3 except the router is no longer trained by a loss function. Now it's trained using a loss-free function optimization technique using biases for the expert. So that's the main difference, and we just expert what that is. Like biases essentially are choosing the expert. If expert 1 has been working for some time, it's too tired, give it a break, pick expert 2, and then expert 3 is idle. Essentially biases are ways to choose expert based on their loads, and it's a very simple technique, simple mathematical, it's beautiful mathematical technique to choose the expert. They still do talk about those loss functions, but they really don't implement that. The main implementation comes in the training paradigm. Their training paradigm has become substantially more complex. The training infrastructure uses so many technological innovations that we take an entire episode just to talk about those technical innovations. There's so many. So one of the main ones that we talked about in the previous version, in the last episode, was the preventing idleness of the GPUs. Usually GPUs are idle because of the pipeline bubble. So one strategy is to use one forward and one backward, where if the future GPUs are performing a forward pass, make the previous GPUs, which are not now sitting idle, to perform a backward pass. So they have gone ahead of that and used even more advanced architecture to in fact involve every single GPUs that are sitting in the pipeline, so that none of them stay idle. In fact, they start performing forward and backward passes for almost every GPU. Some of the GPUs do remain idle if you look at the matrix that they have posted on their technical paper. But if you see their technical paper, almost all the GPUs are being used almost all the time. So that's a substantial leap in efficiency. And they also go in technical in depth, because during training there's a lot of communication back and forth that happens, and that happens through NVLink, and that has used to be a bottleneck till Nvidia bought this Israeli company called that really improved the communication and brought in a new era of distributed compute clusters to be deployed for large language model training. Without NVLink, that would have not been possible. So now even that communication can slow down training. So what the DeepSeek researchers noticed is that the communication overhead introduced by those cross-node communication caused an inefficient computation to communication ratio of approximately 1:1. So if, let's say, 10 seconds was used for computation, 10 seconds would be spent on communication. That's very inefficient. So they used a combination of different techniques to bring down the communication to the minimum, that they don't let those tensors, the weights, to be shared across multiple GPUs. So that's the main reason for using floating point precision, 8-bit precision, so that all those model weights can be contained within a single GPU. Because if the tensors or the matrices, by tensor I mean the matrices, are spread across multiple GPUs, just to perform a single matrix multiplication will involve multi-GPU communication. That will really slow down, and there will be substantial overhead just to store those model weights. Communication overhead would be so high that it's not worth it, and that pretty much slows down all computation for those enterprise grade higher precision models, because of those inter GPU communication that they need to perform, because they use high precision massive matrices that span multiple GPUs. So that being said, the FP8 training has not without issues. The floating point precision with 8-bit precision has its challenges, while the weights can be 8-bit without losing any kind of clarity or accuracy in the predictive power. They noted that they cannot use a low precision for the embedding module. Embedding module is where you take all your word corpus and embed them, essentially convert the words into the numerical representation. Now, if we use a lower precision for that, guess what? We're not going to capture all the words. Let's say we want to capture 70,000 different words in our language corpus. If precision can only scale up to and has the capacity to store 20,000 words, then those 70,000 words cannot be stored in that embedding dimension, just because we don't have the precision to store. That dimension doesn't have the capacity to store 70,000 words. So no compromise for the embedding module. The same thing for output head, because we don't want to lose precision, because we want to output all those words. Output head cannot have a lower precision because it needs to perform a sweeping output for all possible words, and I need to accommodate as many as possible. And the paper goes in extreme technical depth on how they achieve this kind of scaling, where they're using 8-bit precision for some parts of the model and 32 and 16 bits for some parts of the module. So they have to scale up and scale down the precision, and that causes substantial optimization problems or optimization overhead, and a lot of mathematical manipulations needs to be performed. That's all we have to say about the technical details of these DeepSeek models. We of course glossed over the GRPO, the policy optimization that is implemented in the reasoning model. However, that's a very deep topic that needs a more in-depth treatment, which we will attend to in a future episode after we discuss TRPO and other policy optimization like DPO and proximal policy optimization, PPO, that's routinely used to perform alignment of large language models. For now, that's all we have to say. But right now, what are the main implications of these models that we need to discuss? So let's discuss this very quickly. What are the main use cases of these DeepSeek models? What are the challenges and what are the risks of using these models? So the main risk of using these models, as everyone is saying, is that your data, if you're not using the models locally, and that's the best use case of using the models locally in an air-gapped fashion. Air gap means that you turn off the hardware switch for your internet connection, so no data can go out of your box or whatever computer equipment you're using, so that it's totally air-gapped and no amount of information can flow from these models, which can have Trojan horses. If they do have Trojan horses, they will not be able to communicate your data to their external handlers. So that's one of the risk mitigation strategies that many people say. So the risk is minimal to use the DeepSeek model using local OLAMA in an air-gap fashion. I mean, you don't need to air-gap it, and it's pretty safe. If you really want that peace of mind and that extra layer of security, take off your Ethernet cable or turn off the hardware Wi-Fi switch, and you will have that peace of mind. Now, that being said, the main risk that people are talking about comes from using the largest DeepSeek models that are hosted in China. The main risk comes from using these DeepSeek models, the largest DeepSeek model, the 771 billion parameter model that's hosted on their cloud and that's hosted in China. That's the main risk, that your data will go to China. If you read, their disclaimer says that they can monitor keystrokes and user behavior. In fact, they can monitor everything. So that's not the smartest move. Right now, the best use case of DeepSeek is just to use it locally in air-gap fashion and use it in your RAG pipelines. I think the best use case of these DeepSeek models is to use them locally, at least the quantized versions locally in an air-gap fashion, especially to write emails and spruce up any kind of learning or perform assisted learning or use it as a virtual assistant. It is also very good with math, so you can also use it to teach yourself math, like advanced math, algebra, and whatever your heart desires. However, I do not recommend using DeepSeek for use in enterprise settings. If you have a startup or a mid-sized business, or even if an enterprise architect in a large business, do not use DeepSeek unless you get prior authorization. That is a very risky move, and there are two risks, twofold. The main risk we talked about is the enterprise version will probably use the API to call the cloud service in China, and your data will go to China. So that's one of the main risks. Now your data is being leaked to a foreign nation, but you want your data to stay in your own state, is preferably in the same geographic location, and depends on what kind of regulatory compliance that you need to comply to. If you are EU, you have to keep it within EU. For some data you need to keep within EU, and there are regulatory requirements. You probably are better familiar with it. If you are not, then talk to your compliance officer, and they will, or your compliance office if you have one, and they will inform you what are the compliance requirements of data integrity and data management. So that being said, data leak is not the primary risk. The main risk comes from these models having alignment problems. So these models are extremely restrictive in certain scenarios. For example, if you ask it about Tiananmen Square and certain things which goes against the China or the People's Republic of China, then you will not get the correct answers. And some people are saying that it will slowly nudge people to a revisionist history, and you don't want that. If your use case is teaching, for example, you want to deploy a teaching bot in Africa wherever there is sparsity of good quality teachers and education is of paramount importance, and you want to deploy a bot, and in fact Gates Foundation is doing a lot like that. They have created virtual tutors using AI and large language model, and they have deployed it in Africa, and they can perform the job of a teacher where their teachers are non-existent in remote villages, and that's a very good use case. But you cannot use DeepSeek for those use cases, mostly because it will not give the right history in the right chronological order. It will erase a part of the history. Now, if the use case is to use DeepSeek as a math tutor, that's a completely good use case because there is no censorship when it comes to math. So that would be a great use case for DeepSeek, but DeepSeek cannot be used to teach history, for example, because of the censorship that is built into it. In addition to the post-training where they used our GRPO to perform reinforcement learning and alignment, I'm guessing there is also censorship that is built into it, and they definitely use some form of SFT and they are not revealing it. So the main risk that society faces with these kind of models, that is these models, when these models which are open source and cheap to use, if they do become mainstream, then everyone would be using it, and they will slowly nudge the popular opinion and memory of the society in a direction which would completely revise history. For example, definitely do not use these models as a chatbot, as a backend to a chatbot. Because if your user asks questions which is censored, then this model will not answer correctly. And not only your company will lose credibility, it will have severe backlash. The amount of brand and reputation damage that can bring on would be substantial. That will not cover the cost that you save from using these models. So let's say you save 95% of your cost, but the amount of brand and reputational damage that these models will bring because of the censored form of responses that people will soon find out, and they'll soon realize that we are using DeepSeek as our backend because some of the responses will be censored, then immediately there'll be such a severe backlash. There'll be total brand and reputation damage. So definitely big companies, big brands should not be using these models, and I'm pretty sure they will not use these models. So for now, these models are great as a toy example. For consumers, these are great models for consumers to be used in an air gap fashion, and in fact we can replace OpenAI. And if someone is on a fence and they don't use OpenAI that often, I use OpenAI a lot, like almost all day. I have to do many things with OpenAI, like create architecture and all those things. But if there's some people who use OpenAI to just write letters, DeepSeek quantized models for consumer grade GPUs are a full alternative to OpenAI for writing emails and letters and performing other virtual assistant tasks. So if someone is using OpenAI, ChatGPT or Claude just as a virtual assistant, then DeepSeek is a complete replacement as it is right now. Yes, there are certain caveats, certain blind spots. It is not very good at writing big essays and optimized LinkedIn articles that Claude and OpenAI can do. So if you are on the fence, get rid of those, stop paying for those and start using DeepSeek. If you just need a virtual assistant, DeepSeek is your model. My recommendation is use DeepSeek on your local computer as your virtual assistant and nothing more. Do not deploy this model. Do not use it as a use case or an app for your startup or your company. Do not use it in an enterprise setting. Totally block this model from any kind of use in a business setting and you'll be fine. So that's all we have to say for this episode. We have covered a lot of ground and covered the entire gamut of DeepSeek models from version 1 to R1 model. So that's a series of 5-6 models that we have covered in substantial amount of technical depth, and that's a lot of ground that we have covered together. Thanks for listening and see you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.